Tonight, we are going to talk about the giant planets we were taught to imagine as simple worlds. Huge balls of gas, beautiful stripes, rings, blue clouds, distant, cold, and mostly empty. But the deeper we study them, the less simple they become. Jupiter is not just the biggest planet. It is a storm-covered world with pressures so extreme that hydrogen may behave like metal deep inside it. Saturn is not just a planet with rings. Its rings are a temporary, delicate system made of countless icy fragments, while its moons may be more interesting than the planet itself. Uranus does not simply roll through space as a blue-green marble. It spins almost sideways, with a magnetic field that refuses to line up neatly. And Neptune, the farthest giant, receives almost no sunlight, yet still drives some of the fastest winds in the solar system. These worlds are not oversized versions of Earth. They are alien machines of pressure, chemistry, storms, rings, moons, and hidden interiors. Before we begin tonight's journey, subscribe to the channel if you want more calm space documentaries like this. Leave a like if you enjoy slow journeys through the universe, and write in the comments where you are watching from and what time it is where you are right now. It is strange to think that people are listening from different parts of one small planet, while the giant worlds move silently far beyond us. Tonight, you are watching the Space for Sleep channel, talking about the gas giants are stranger than you were taught. The simple version begins with 4 names: Jupiter, Saturn, Uranus, Neptune. Most people learn them early, almost like a rhyme at the edge of the solar system. Mercury is hot, Venus is cloudy, Earth is home, Mars is red. Then, beyond the asteroid belt, the planets become huge, cold, distant, and strange. Jupiter is the biggest one. Saturn has rings. Uranus is tilted. Neptune is blue. That version is not completely wrong. It is just too small. It turns 4 of the most alien worlds in the solar system into a set of classroom labels. The planets become simple icons, easy to remember and easy to underestimate. A striped giant, a ringed giant, a sideways giant, a faraway blue giant. But nothing about these worlds is simple once we leave the textbook picture behind. The first correction comes before we even reach the planets themselves. People often call all 4 outer giants gas giants. In ordinary conversation, that phrase is familiar and useful, because these worlds are enormous compared with Earth, and they do not have solid surfaces like the rocky planets. But scientifically, the family is split in 2. Jupiter and Saturn are the true gas giants. Uranus and Neptune are ice giants. That does not mean Uranus and Neptune are frozen balls of ordinary ice. The word ice in planetary science points toward materials such as water, ammonia, and methane, substances that may behave in exotic ways under enormous pressure and heat. Deep inside those planets, the conditions are nothing like an ice cube in a glass. They are dense, hot, compressed, and still not fully understood. Already, the school version begins to crack. The outer planets are not just bigger Earths. They are not rocky worlds wearing thick atmospheres. They are not places where a spacecraft could descend through clouds, break through a final layer, and land on a normal surface. For Jupiter, Saturn, Uranus, and Neptune, the idea of surface becomes slippery. On Earth, surface means something obvious. The ground is where the air ends and the solid planet begins. You can stand on it. You can draw a line between sky and land. On the giant planets, that simple boundary disappears. There may be no hard surface at all in the ordinary human sense. A spacecraft falling into Jupiter would not pass through clouds and then touch a ground like a continent. It would sink into deeper and deeper pressure. Gas would become denser. Temperature would climb. The atmosphere would slowly stop behaving like the air we know and begin behaving more like a strange, crushing fluid world. Eventually, the spacecraft would be destroyed long before it found anything like a place to stand. That alone makes the word planet feel different. A planet does not have to offer ground. A planet can be a vast atmosphere, wrapped around an interior, where pressure writes the rules. It can be a world without a human-scale boundary, a place where falling downward does not lead to soil, but to heat, density, and conditions that break machines apart. The 4 giant planets teach that lesson in different ways. Jupiter and Saturn are dominated by hydrogen and helium, the 2 lightest elements, the same ingredients that fill most of the Sun. Uranus and Neptune contain hydrogen and helium too, but their compositions include larger fractions of heavier volatile materials, which is why they sit in the ice giant category. Their sizes, masses, colors, magnetic fields, heat flows, moons, rings, and interiors all tell different stories. The easy phrase, gas giant, hides a whole family of differences. That is where the video really begins. Not with the claim that school was useless. School gave us the map. The problem is that maps simplify. A school diagram has to make the solar system fit on a page. It has to turn unimaginable distances into neat spacing, compress planetary sizes into clean circles, and give each planet one memorable identity. The giant planets are shown as colored balls because that is the only way to make them easy to learn. But the real solar system does not care about being easy. Jupiter is not simply a large striped sphere. It is a world more massive than all the other planets combined. A planet with a deep atmosphere, violent storms, a huge magnetic environment, and moons that could each deserve their own documentary. Saturn is not merely the planet with rings. It is a low-density giant with delicate icy structures surrounding it, a moon system filled with surprises, and places like Titan and Enceladus that changed how scientists think about habitability far from the Sun. Uranus is not just the planet that rotates on its side. It is a cold, underexplored ice giant with an offset magnetic field, strange seasons, and an interior that may hold clues to an entire class of planets commonly found around other stars. Neptune is not simply blue because it is far away and cold. It is the most distant known planet. Yet its atmosphere is active, its winds are extreme, its storms appear and vanish, and its moon Triton looks like a captured world from the outer solar system. Each giant is more than one planet. Each is a system. Rings, moons, magnetic fields, storms, radiation belts, hidden interiors, gravity sculpting nearby space. The outer planets do not sit quietly at the edge of the solar system like decorations. They shape the architecture around them. Their gravity affects small bodies, moons, rings, comets, and ancient debris. Jupiter in particular has influenced the movement of countless objects over the history of the solar system. Neptune's gravity helped shape the distant region where Pluto and other icy bodies orbit. The giants are not background. They are engines of structure. Part of the reason we underestimate them is that distance makes them calm. From Earth, even Jupiter is only a bright point to the naked eye. Saturn looks like another bright star unless a telescope reveals its rings. Uranus and Neptune are so distant that their true nature remained hidden for most of human history. The eye reduces them. Spacecraft undo that reduction. At Jupiter, Saturn, Uranus, and Neptune, missions and telescope observations revealed active atmospheres, rings, moons, magnetic fields, and deep interiors that cannot be explained by a simple classroom label. That lack of data matters. The planets we call familiar are not equally known. Jupiter and Saturn have received orbiters. Uranus and Neptune have not. For the ice giants, much of what we know still comes from one fast spacecraft encounter decades ago, combined with telescope observations from Earth and space. So the outer solar system is familiar in name and unfinished in detail. That is the perfect place for misunderstanding. A simple classroom label can survive for years because most people never return to the subject. Gas giants becomes a mental box. Inside it, everything beyond Mars is huge, cold, and cloudy. The differences blur. Jupiter and Neptune feel like members of the same basic category, just with different colors. The truth is more interesting. Jupiter and Saturn may reveal what happens when a young planetary core gathers a massive hydrogen-helium envelope from the solar nebula. Uranus and Neptune may reveal what happens when planets form with less gas, more heavy material, different histories, and interiors shaped by substances that behave strangely under pressure. That distinction is not a technical detail hiding in the background. It changes the story of planet formation. Why did Jupiter and Saturn become true gas giants, while Uranus and Neptune ended up smaller and richer in heavier materials? Did they form where they are now? Did they move? How did the early solar system arrange itself into this final structure? Why are planets similar in size to Uranus and Neptune so common around other stars, while in our own system we have only two close examples, both still underexplored? The four outer giants are not just planets we memorized. They are evidence. They carry clues about the birth of the solar system, the movement of early planets, the behavior of matter under extreme pressure, and the kinds of worlds that may be common throughout the galaxy. Jupiter's atmosphere keeps changing. Saturn's rings evolve. Uranus moves through strange seasons because of its extreme tilt. Neptune forms dark storms far from the warmth of the sun. Even the word cold can mislead. The outer planets receive far less sunlight than Earth, especially Uranus and Neptune. Yet lack of sunlight does not mean lack of activity. Giant planets hold internal heat. Some give off more energy than they receive from the sun. Their deep interiors remember formation, contraction, separation of materials and processes still not fully solved. A world can be far from the sun and still not be quiet. That is one of the most important ideas to carry forward. This is why the journey through them has to begin with humility. The names are familiar. The worlds are not. The first step is to stop imagining these worlds as colored balls in a row. Jupiter is not a ball you could land on. Saturn's rings are not smooth, solid hoops. Uranus is not strange only because it is tilted. Neptune is not calm because it is far away. Their moons are not minor accessories. Their interiors are not fully mapped. Their magnetic fields are not simple copies of Earth's. The outer giants are more like laboratories built by gravity. They test matter at pressures we cannot casually reproduce. They build weather systems larger than Earth. They hold moons with oceans, volcanoes, atmospheres, and possible chemical environments worth searching. They keep rings that may be young, temporary, and constantly shaped by tiny gravitational pulls. They show us what planetary systems can become when mass, distance, chemistry, and time work together. That is the real correction to what we were taught. Not that the old facts were false, that they were only the first layer. The deeper we go, the less these planets feel like simple categories. The phrase, gas giant, begins to give way to something larger. Giant worlds, each with its own physics, its own history, its own unanswered questions. And the natural place to begin is with the largest of them all. Jupiter looks familiar because it dominates so many pictures of the solar system. Its bands are iconic. Its great red spot is famous. Its size is almost a symbol of planetary power. But even Jupiter, the planet everyone thinks they know, becomes stranger the moment we ask a basic question. If there is no normal surface, what is Jupiter actually like beneath the clouds? If there is no normal surface, then Jupiter has to be understood in a different way from the rocky planets. Earth gives us a useful illusion. It lets us imagine planets as solid bodies with atmospheres placed on top of them. Air above, ground below, a clear boundary between the two. Mars works that way too, even though its air is thin and cold. Venus hides its surface under clouds, but the surface is still there. Mercury has almost no atmosphere at all, so the idea is even simpler. A rocky world exposed to space. Jupiter breaks that habit. A spacecraft descending into Jupiter would not experience a clean moment where sky ends and planet begins. It would pass through cloud layers, thicker air, higher pressure, rising temperature, and then into material that no longer fits ordinary words easily. Gas becomes dense. Hydrogen and helium are squeezed into deeper states. The deeper the spacecraft falls, the less Jupiter resembles anything humans have stood on. There is no beach, no desert, no mountain range waiting under the clouds. Only more Jupiter. That is why calling it a planet can make it feel too familiar. Jupiter is a planet, but it is not a world built around human ideas of land. It is closer to a gigantic pressure system, wrapped around a deep interior that scientists can only infer from gravity, magnetism, heat, and spacecraft measurements. The first number is already difficult to hold in the mind. Jupiter is more massive than all the other planets in the solar system combined. Not just bigger in diameter, not just wider in photographs, but more massive than Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury, and every other planet put together. Its gravity dominates the outer architecture of the solar system in a way no other planet can match. Yet, Jupiter is still not a star. That detail matters, because Jupiter is sometimes described as a failed star, but that phrase can be misleading. It is made mostly of hydrogen and helium, like the Sun, and it is enormous compared with Earth. But it never reached anything close to the mass needed for sustained hydrogen fusion in its core. It is not a star that almost happened. It is a planet that grew large enough to capture a huge envelope of the early solar system's lightest gases. That makes Jupiter a time capsule. The Sun contains most of the original material of the solar nebula, but the Sun is also a nuclear furnace. Jupiter kept a large sample of the nebula in planetary form. Its composition can tell scientists something about the gas and dust from which the solar system formed. In that sense, Jupiter is not only the largest planet, it is a surviving record of the beginning. But the record is not easy to read. From outside, we see colored bands and storms. Beneath those cloud tops, the planet becomes a mystery of pressure. The upper atmosphere is mostly hydrogen and helium, with smaller amounts of methane, ammonia, water, and other compounds. Those trace chemicals help create the cloud colors and layers we see. They are important visually, but they are not the main mass of the planet. The main story is hydrogen. On Earth, hydrogen is familiar as a gas, light enough to escape from a balloon, and simple enough to appear in school chemistry. Inside Jupiter, pressure forces hydrogen into states that do not exist naturally at Earth's surface. Go deep enough, and scientists expect it to become metallic, meaning it conducts electricity in ways ordinary molecular hydrogen cannot. This is one of Jupiter's central secrets. Far below the visible clouds, a deep layer of electrically conducting hydrogen may help drive the planet's enormous magnetic field. Jupiter spins quickly, rotating once in about 10 hours despite its huge size. In that fast-spinning interior, conducting material can act like a dynamo, generating a magnetic field far stronger than Earth's. That kingdom is dangerous. Spacecraft sent to Jupiter have to be designed with radiation in mind. Juno, the spacecraft currently studying Jupiter, follows an elongated polar orbit, partly to reduce exposure to the worst regions of radiation. Even machines have to treat Jupiter with caution. A probe falling into Jupiter would eventually be crushed, heated, and destroyed. NASA's Galileo mission gave a real example of this. In 1995, the Galileo atmospheric probe entered Jupiter's atmosphere and sent back data as it descended. It survived for less than an hour before the pressure and heat ended the transmission. That was a machine designed for the plunge. It did not find a ground. It found deeper atmosphere. That descent changed Jupiter from an image into a place, but only for a brief distance. The rest remains hidden. Juno continues that work from orbit by measuring Jupiter's gravity and magnetic fields, trying to infer what lies below the clouds. One of the most important surprises from Juno is the idea that Jupiter's core may not be a neat solid ball, separated clearly from the surrounding layers. The data suggests something more diffuse, often described as a diluted or fuzzy core, where heavy elements may be mixed through a larger region. That is a major shift from the simple picture. In a classroom diagram, a planet often has layers like a cut fruit: crust, mantle, core. Even gas giants may be drawn with a tidy central core and shells around it. Jupiter does not seem to obey such clean simplicity. Its deep interior may blur boundaries. Its formation may have involved collisions, mixing, dissolution, or a slow rearrangement of heavy material under immense pressure. The deeper scientists look, the less Jupiter resembles a neat diagram. That is the pattern with giant planets. Their outer beauty hides a deeper refusal to be simple. Even the question of heat changes the story. Jupiter is far from the Sun, but the Sun is not the only source shaping it. Jupiter radiates more energy into space than it receives from sunlight. This extra heat comes from the planet's long, slow cooling and contraction since formation. Gravity built Jupiter, and some of that ancient energy is still leaking away. The planet is still releasing its beginning. That internal heat helps drive atmospheric motion. It does not explain every detail of Jupiter's weather, but it reminds us that the planet is not passive. It is not merely being warmed from outside, it is also cooling from inside, with deep energy moving upward through a world of clouds, storms, fluids, and pressure. From Earth, sunlight feels like the main engine of weather. The sun warms the ground and ocean. Air moves. Storms form. Jupiter receives much less sunlight than Earth, but its interior keeps contributing energy. Its atmosphere is shaped by both the weak sun and the planet's own internal heat, combined with fast rotation and complex chemistry. That is why Jupiter can host storms larger than Earth. But before we reach those storms, the interior has to be taken seriously. Without the deep planet, the visible planet makes less sense. The stripes, jet streams, storms, lightning, magnetic field, and heat are not separate facts. They are surface expressions of a world whose scale and composition are unlike anything in the inner solar system. Jupiter is what happens when a planet keeps most of its mass in hydrogen and helium, grows massive enough to crush that material into exotic states, spins fast enough to organize its atmosphere into bands, and holds enough internal heat to remain dynamic billions of years after formation. A bigger Earth would not do that. Scaling Earth up does not produce metallic hydrogen, a planet-wide magnetic monster, and cloud systems driven by a deep fluid interior. Jupiter belongs to a different category of planet, where mass changes the rules. The difference begins with gravity. On Earth, gravity holds an atmosphere but leaves a solid surface available. On Jupiter, gravity compresses the planet itself into deeper and deeper states. Pressure increases so dramatically that ordinary categories begin to fail. Gas, liquid, metal, atmosphere, interior, the boundaries do not behave like household words. If we say it is a ball of gas, we are not completely wrong, but we invite the wrong image. A ball of gas sounds light, soft, and almost empty. Jupiter is not empty. It is dense enough, deep enough, and massive enough to crush spacecraft, reshape hydrogen, and create a magnetic field that dominates millions of kilometers of space. The phrase ball of gas is too gentle. Jupiter is a world of compressed fluid and invisible force. From the outside, its cloud tops rotate in bands. Below them, pressure grows. Below that, hydrogen changes. Somewhere deeper, heavy elements may be distributed through a diluted core. Around the planet, the magnetosphere traps radiation and interacts with its moons. Above it, auroras glow near the poles, fed by charged particles and magnetic power. Everything connects. The atmosphere is not decoration. The interior is not just hidden mass. The magnetic field is not just another fact in a list. Jupiter is a connected machine, built from rotation, gravity, heat, chemistry, and deep pressure. That is why it cannot be treated as simply the biggest planet. Being the biggest is the least interesting thing about it. The more important fact is that Jupiter shows what planet can mean when mass changes matter itself. The stripes are no longer painted bands. The great red spot is no longer just a famous oval. The lightning, clouds, jet streams, and polar storms are not isolated curiosities. They are the visible weather of a planet whose hidden interior is already more alien than the school version ever suggested. So after asking what Jupiter is beneath the clouds, the next step is to look back at the clouds themselves. Because the part of Jupiter we can see is not calm either. It is a moving atmosphere of belts, zones, storms, and winds, where weather can outgrow Earth and last longer than human civilizations. That weather begins as a pattern almost everyone recognizes. Jupiter's face is covered in bands. From far away, they look painted on, as if the planet has been wrapped in stripes of cream, rust, white, and brown. In school diagrams, those stripes are usually treated like decoration. They make Jupiter easy to identify. They give the largest planet its familiar look, but the bands are not decoration. They are weather. Jupiter's visible atmosphere is divided into bright zones and darker belts, each one moving in relation to the others. The planet rotates so quickly that one day on Jupiter lasts only about 10 hours, and that fast rotation helps stretch storms and clouds into long east-west ribbons around the globe. Instead of weather systems moving across continents and oceans, Jupiter has no solid surface to interrupt them. There are no mountains to break winds, no seas and deserts to divide heat in familiar ways, no ground to anchor a storm the way Earth does. The whole visible planet is atmosphere in motion. That is the first thing the school picture hides. When we look at Jupiter, we are not looking at a surface with weather above it. We are looking directly at the weather itself, the top layer of a deep, moving world. On Earth, a storm forms in a thin layer of air above the ground and ocean. On Jupiter, the weather sits above an interior with no normal surface, overpressures and depths that make the atmosphere feel less like a blanket and more like the outer expression of the planet itself. Clouds are not floating over a familiar world. They are part of a world where the distinction between sky and planet has already become unclear. The bands mark powerful jet streams. Some flow east, others flow west. Between them, vortices and storms can survive for astonishing lengths of time. On Earth, a hurricane can be devastating, but it eventually loses its structure when it crosses land or colder water. Jupiter does not offer that kind of simple end. With no continents beneath it, and with energy moving through a deep atmosphere, storms can last far longer than our weather instincts expect. That is why Jupiter's most famous feature is not a mountain, a canyon, or a sea. It is a storm, the Great Red Spot. Even the name sounds almost too gentle for what it is. A spot feels small. On Jupiter, the spot is an enormous anticyclonic vortex, a rotating storm system large enough to dominate the planet's southern hemisphere in images. It has been monitored since the 19th century. and perhaps connected to observations even earlier, although the exact history of the current storm is more complicated than the simple claim that it has been unchanged for centuries. That complexity matters. The Great Red Spot is not a permanent painted mark. It changes. It has been shrinking in modern observations. Its shape, color, speed, and surrounding activity can vary. In 2017, NASA's Juno data placed its width at about 16,350 kilometers, roughly 1.3 times Earth's diameter at that time. Later observations and studies continue to show a storm that is dynamic, not frozen. The lesson is not that Jupiter has one eternal scar. The lesson is that Jupiter's atmosphere can keep a storm alive for a time longer than recorded human weather history. A storm larger than Earth can persist in a giant planet's atmosphere while civilizations rise, build telescopes, launch spacecraft, and still keep watching it change. For a long time, the Great Red Spot was mostly a visible mystery. Telescopes could track its shape and color. Spacecraft could photograph it in extraordinary detail. But the question of depth remained harder. Was it only a shallow weather feature sitting near the cloud tops, or did it reach far down into Jupiter's atmosphere? Juno helped change that question. By measuring gravity and using microwave instruments, Juno gave scientists a way to probe below the visible clouds. NASA has reported that the Great Red Spot extends hundreds of kilometers below the cloud tops, with results constraining its depth to roughly 300 miles, or about 500 kilometers. In some summaries, that does not mean the storm reaches the center of Jupiter. It means the visible oval is not just a thin-colored skin on the planet. The storm has roots, not roots in the ground, because Jupiter has no ground in the Earth-like sense. Roots in atmosphere, depth in weather. That idea changes the way the image feels. The Great Red Spot is not only something sitting on Jupiter, it is a structure embedded within the planet's moving atmosphere, reaching downward through layers of pressure and temperature that our eyes cannot see. The familiar oval becomes a window into the depth of the weather. Around it, smaller storms swirl, merge, shear, and break apart. White ovals appear, brown barges drift. Turbulent wakes trail behind features as winds on different sides move at different speeds. In close-up images from Juno, Jupiter stops looking like a smooth striped ball and begins to look like a turbulent fluid painting. All curls, eddies, folds, and rotating cells. The beauty is real. So is the violence. Winds inside Jupiter's atmosphere can move at hundreds of kilometers per hour. Different bands slide past each other in opposite directions. Storms form at boundaries where motion changes. The atmosphere is organized and chaotic at the same time, like a machine that never stops turning, but never repeats exactly. This is why Jupiter is not only a planet with weather, it is a weather planet. The visible globe is dominated by atmospheric motion on a scale no Earth storm can match. Even Earth's most powerful hurricanes are small when placed against Jupiter's belts and zones. A hurricane on Earth is shaped by ocean heat, rotation, moisture, land, and pressure differences. Jupiter's storms are shaped by rapid rotation, internal heat, chemical clouds, deep atmospheric layers, and the absence of any surface that would make them behave like ours. Jupiter also has lightning. That detail can surprise people because lightning feels like an Earth phenomenon, tied to thunderstorms, rain clouds, and familiar weather. But spacecraft have detected lightning on Jupiter, and Juno has revealed that storms and cloud processes there are more complex than a simple ammonia cloud deck. Water may play an important role deeper in the atmosphere, because water clouds and moist convection can help drive powerful storms. The clouds themselves form at different depths, depending on temperature, pressure, and chemistry. Ammonia clouds can appear high in the atmosphere. Deeper layers may involve ammonium hydrosulfide and water clouds, These are not decorative colors placed over the same basic air we breathe. They are chemical layers in a hydrogen-helium atmosphere. A visible image of Jupiter is not the whole atmosphere. It is the top of a deep system. Juno's observations suggest that ammonia, storms, and circulation below the clouds are more complicated than a calm layered diagram would imply. Again, the school image breaks. The stripes are not flat. The clouds are not a painted skin. The famous storm is not only a colored oval. The great red spot carries another kind of lesson, because it reminds us that even iconic planetary features may not last forever. The storm is huge by Earth standards, but it is not immune to change. It has been shrinking, and scientists continue to study why. Smaller atmospheric features can interact with it. Jet streams may feed or confine it. Its color may depend on chemical reactions high in the atmosphere, possibly involving sunlight acting on compounds brought upward from below, though the exact source of its red color is still not fully settled. That uncertainty should not be turned into fake mystery. It is simply a real scientific problem. A red storm has been visible for generations, yet its exact color chemistry, formation history, and future are not perfectly known. That is not because scientists are careless. It is because Jupiter is hard. The planet is enormous, remote, dynamic, and layered. Observations improve slowly, mission by mission, instrument by instrument. Even the most famous storm in the solar system still has unanswered questions. A simple label like biggest planet cannot carry all of that. Neither can gas giant. If we use it lazily, Jupiter is a gas giant, but the word gas does not mean soft, simple, or empty. Its gas is under gravity. Its atmosphere is deep. Its storms are planetary. Its pressure changes matter. Its heat leaks from an ancient formation history. Its magnetic field stretches far into space. The planet is not sitting still behind its bands. It is working. That work is what makes Jupiter so visually hypnotic. The stripes are the surface of motion. The great red spot is a storm surviving inside a moving world. The polar cyclones are structures at the edge of a planet, spinning too quickly for Earth intuition. The lightning hints at deeper clouds and water. The turbulent swirls show that the atmosphere is not a static painting, but a living fluid system. In a calm telescope view, Jupiter can seem almost peaceful. In reality, it is violent, without needing to be dramatic. No flames, no solid ground cracking, no ocean waves breaking against a shore. Just endless atmosphere moving over endless atmosphere, with storms deep enough to reshape what we thought visible weather could be. That is why Jupiter is the right first giant. It takes the simplest school label, the biggest planet, and turns it into a question about matter, pressure, weather, magnetism, and time. The more we study it, the less it behaves like a larger version of anything familiar. And yet Jupiter's strangeness does not end at Jupiter. Some of the most important places in its system are not inside the planet at all. They orbit around it. 4 large moons, first seen by Galileo in 1610, changed the history of astronomy, because they prove that not everything orbited Earth. Today, those same moons matter for a different reason. They show that a giant planet can create worlds as strange and important as itself. The atmosphere of Jupiter teaches us that the planet is not a simple ball. Its moons teach us that Jupiter is not only a planet, it is a miniature system, with volcanic worlds, icy oceans, magnetic surprises, and ancient surfaces held in the grip of its gravity. That miniature system begins with 4 bright points. In 1610, Galileo Galilei turned a small telescope toward Jupiter and noticed something that did not fit the old picture of the universe. There were tiny points of light near the planet, and over several nights, they changed position. They were not fixed stars behind Jupiter. They were moving with it. They were moons. Io, Europa, Ganymede, Callisto. Today, they are called the Galilean moons, and it is easy to forget how much they changed. Their discovery showed that not everything in the sky orbited Earth. Jupiter had its own small system, its own moving family, its own world circling a giant planet far from the center of human life. Those 4 moons are not just dots beside Jupiter. They are places. Each one is large enough to have a history, a surface, an interior, and a reason scientists still care about it. Together, they turn Jupiter from one planet into something closer to a miniature solar system. This is another place where the school version becomes too small. The simple version says Jupiter has many moons. The deeper version says Jupiter's gravity has built a system of worlds that are more varied than many planets. The innermost of the 4 is Io, and Io is almost the opposite of what people expect from a moon. The word moon often suggests something cold, silent, cratered, and ancient. Earth's moon feels like a frozen memory of impacts and dust. Io is not like that. Io is alive with volcanoes. Not alive biologically, but geologically restless, in a way that makes it one of the most violent, solid worlds we know. It is the most volcanically active world in the solar system, with hundreds of volcanoes and lava flows that can reshape its surface. Instead of a quiet gray sphere, Io appears yellow, orange, black, white, and red, colored by sulfur and volcanic materials spread across the ground. The reason is not sunlight, it is gravity. Io orbits close to Jupiter, inside the pull of an enormous planet, and in a gravitational relationship with Europa and Ganymede. Those orbital interactions keep Io's path slightly stretched instead of perfectly circular. As Io moves around Jupiter, tidal forces flex it. The moon is squeezed and released, over and over again. That flexing creates heat, enough heat to melt rock, enough heat to power volcanoes across the surface. On Earth, volcanism is driven by internal heat, plate tectonics, mantle processes, and the planet's own geological evolution. On Io, the engine is partly external. Jupiter's gravity helps knead the moon from the outside, turning orbital motion into internal heat. That is a strange idea. A moon can be heated by the planet it orbits. Its geology can be powered by gravity. Io shows that a giant planet does not only hold moons in place, it can change them from within. This is why Jupiter's moons matter. They are not passive companions. They are shaped by the giant planet's gravity, radiation, and magnetosphere. In return, they affect the space around Jupiter. Io, especially, feeds material into Jupiter's magnetic environment, creating a torus of charged particles around the planet. The moon and the giant are linked physically and electrically across space. Io is beautiful, but it is not a promising home for life as we know it. Its surface is battered by radiation and reshaped by extreme volcanism. Yet it teaches a lesson that becomes crucial for the next moon outward. Tidal heating can keep a world active, far from the sun. Europa takes that lesson and turns it into one of the most important questions in planetary science. At first glance, Europa looks calmer than Io. Its surface is bright, icy, and crossed by long reddish-brown lines. It does not look like a volcanic furnace. It looks frozen, smooth in some areas, fractured in others, almost like a cracked shell. For a long time, that icy shell was the clue. Europa's surface has relatively few large craters, suggesting that it has been renewed in geological terms. Ridges, bands, and fractured terrain point toward movement in the ice. Magnetic measurements from the Galileo mission also supported the idea of a conducting layer beneath the surface, consistent with a salty subsurface ocean. The picture that emerged is extraordinary. Europa may have a global ocean beneath its ice, not a lake, not a small pocket of meltwater. a hidden ocean, possibly containing more water than Earth's oceans, trapped below a frozen crust and kept liquid by internal heat. Sunlight at Jupiter is much weaker than at Earth, but Europa does not need the sun to warm an open sea. Tidal flexing from Jupiter can help provide energy inside the Moon. Europa is one of the reasons the search for life changed. For a long time, people imagined habitability mostly as a matter of being Earth-like on the surface. A rocky planet, the right distance from its star, liquid water under open sky. Europa shows another possibility. An ocean world hidden beneath ice, far from the sun, warmed by gravity, sealed away from direct sunlight. This is why NASA's Europa Clipper mission matters. Launched in 2024, it is designed to make repeated flybys of Europa while orbiting Jupiter, studying the Moon's ice shell, composition, geology, and habitability. It will not land or drill into the ocean. Its job is more careful. Determine whether Europa has environments beneath its surface that could support life. That wording matters. Could support life is not the same as contains life. Europa is powerful enough without exaggeration. A moon around Jupiter, far from the Sunday, may hide an ocean below its frozen surface. Then comes Ganymede. If Europa is the ocean question, Ganymede is the scale question. Ganymede is the largest moon in the solar system. It is bigger than Mercury, though less massive. If it orbited the Sun directly, many people would instinctively call it a planet. Instead, it orbits Jupiter, which makes it a moon by relationship, not by smallness. Its surface is a mix of dark ancient regions and brighter grooved terrain. Like Europa and Callisto, Ganymede may also contain a subsurface ocean, possibly layered between ice phases deep inside. But one feature makes it unique among moons. Ganymede has its own magnetic field. That is extraordinary. Earth has a magnetic field. Jupiter has a huge one. But a moon with an intrinsic magnetic field is rare enough that Ganymede stands alone in the solar system. It suggests a differentiated interior and a dynamo process, likely involving conducting material inside the moon. So around Jupiter there is a moon large enough to be planetary in scale, possibly ocean-bearing, with a magnetic field of its own, moving inside the far larger magnetosphere of Jupiter. A magnetic world inside a magnetic world. Ganymede is also a major target for ESA's JUICE mission, which launched in 2023 and is planned to study Jupiter and its icy moons, with special attention to Ganymede. The mission reflects a broader truth. The outer solar system is no longer only about planets. The moons have become central scientific destinations. The fourth Galilean moon, Callisto, is quieter at first. It is heavily cratered, dark, ancient-looking, and distant enough from Jupiter that it is not flexed as violently as Io or Europa. Compared with the other three, Callisto can seem less dramatic. It does not have Io's volcanoes. It does not have Europa's famous cracked ocean world image. It does not have Ganymede's size record and magnetic field. But Callisto matters because old surfaces are records. Its battered terrain may preserve a history of impacts from the early solar system, where Io is constantly renewed and Europa may be geologically active beneath ice. Callisto carries the appearance of a world that has held on to scars for billions of years. Even here, however, the simple picture is not enough. Scientists have considered evidence that Callisto may also have a subsurface ocean. If so, then 3 of Jupiter's 4 large moons may contain hidden liquid water in some form, while the innermost is a volcanic world heated by tides. Io, volcanoes. Europa, a hidden ocean. Ganymede, the largest moon, possibly ocean-bearing, with its own magnetic field. Callisto, an ancient cratered world, perhaps also hiding water beneath its surface. This is why calling them moons can make them feel too minor. They are worlds orbiting a world. Jupiter is a center of activity. The Galilean moons orbit within its influence like 4 different experiments in planetary evolution. Put them around the Sun instead of Jupiter, and some of them would be discussed like planets. Around Jupiter, they become a family, and the family reveals how gravity can create diversity. Europa, and perhaps Ganymede and Callisto, remind us that liquid water can hide where the old-school diagrams would never make us look. Io reminds us that gravity can heat a world until rock melts. The giant planet system becomes a laboratory for the idea that planets and moons are shaped not only by their distance from the Sun, but by the gravitational relationships around them. Its influence reaches into the interiors of its moons, into magnetic interactions, into radiation belts, and into orbital resonances that keep worlds from settling into simple stillness. The giant planet is not just being orbited, it is participating in the lives of its moons. That is why the outer solar system feels less empty the more we study it. Far from the Sun, where old thinking might expect frozen dead worlds, we find volcanoes, oceans, magnetic fields, and chemical possibilities. Distance from the Sun does not mean distance from activity. The Galilean moons also prepare us for Saturn, because Saturn will repeat the lesson in its own way. At Jupiter, the planet itself first appears as the main subject, and then its moons complicate the story. At Saturn, the same thing happens with even more visual force. Everyone sees the rings first. They dominate the image so completely that Saturn becomes almost impossible to imagine without them. But as with Jupiter's stripes, the familiar picture can be misleading. Saturn's rings are not solid hoops. They are not permanent metal bands. They are not simple decorations around a calm planet. They are made of countless icy particles shaped by gravity, moons, collisions, waves, gaps, and time. Jupiter's moons teach us that a giant planet can become a system of worlds. Saturn's rings will teach us that even beauty in the outer solar system can be temporary, fragile, and far stranger than it looks in a classroom diagram. Saturn's rings teach a different lesson from Jupiter's moons. They look obvious. They look simple. Even through a small telescope, Saturn appears almost unreal. A pale golden planet surrounded by a clean, flat ring. It is one of the few sights in astronomy that can make a person understand instantly why people kept looking upward before they knew what space really was. Saturn does not need explanation to feel beautiful. That beauty is part of the problem. The rings look so perfect that the mind turns them into an object. A hoop, a disk, a smooth, solid structure wrapped around a planet. But Saturn's rings are not solid. They are not a single band. They are not permanent jewelry placed around the planet at the beginning of time. The closer we study them, the more fragile they become. They are made of countless individual particles, mostly water ice, mixed with darker rocky or dusty material. Some particles are tiny grains, others are chunks, boulders, or larger pieces. Each one is orbiting Saturn on its own path, held by gravity, shaped by collisions, disturbed by moons, and slowly changed by time. From far away, they merge into a clean, bright ring. Up close, the ring is a swarm. That is the first strange truth about Saturn. Its most famous feature is not one thing at all. It is billions upon billions of separate pieces moving together so precisely that from Earth, they become a single icon. The smoothness is an illusion made by distance. The rings are also thin in a way that feels almost impossible. They stretch outward for hundreds of thousands of kilometers, yet their vertical thickness is tiny compared with their width. A structure can be wide enough to dominate the image of a planet and still be thin enough, on its own scale, to feel like a sheet of light. Some parts are dense, others are faint. There are broad-named regions, like the A ring, B ring, and C ring. There are gaps, waves, edges, spokes, narrow ringlets, and disturbances created by gravitational interactions. The rings are not smooth because nothing is happening. They are smooth because countless small events average into beauty at a distance. Moons help write the pattern. Small moons can act like shepherds, shaping narrow rings and keeping particles confined. Other moons create gaps or waves through orbital resonances, where repeated gravitational tugs organize material over time. A moon does not have to crash through the rings to shape them. Gravity is enough. This is one of the most elegant parts of the Saturn system. The rings are not only particles orbiting a planet, they are particles responding to a whole gravitational orchestra. Saturn, nearby moons, distant moons, collisions, tides, and tiny disturbances that build visible structure. The result looks still. It is not still. Cassini showed that Saturn's rings are full of detail. The spacecraft spent years orbiting Saturn, studying the planet, rings, and moons with a closeness no telescope on Earth could match. During the mission, the rings stopped being a famous outline and became a complex physical environment. Cassini saw vertical structures at ring edges, waves caused by moons, propeller-shaped disturbances made by small embedded objects, and changing features called spokes across parts of the rings. The school version says Saturn has rings. The real version asks how rings live, age, lose material, and remember events that may have happened long before humans existed. The origin of Saturn's rings remains one of the great questions. One possibility is that the rings are the remains of a shattered moon, comet, or icy body that came too close to Saturn and was torn apart by the planet's gravity. Another idea, supported by some recent simulations, is that the rings may have formed from debris after icy moons collided. Scientists still debate the exact story, because ring origin depends on mass, composition, age, contamination by dust, and how the system has evolved. That uncertainty is important to say clearly. Saturn's rings are not fully explained. They are not a solved decoration. Their brightness suggests they may be relatively young compared with Saturn itself, because over billions of years, micrometeorite dust should darken icy material. Cassini's measurements of ring mass and composition strengthened the idea that the rings could be much younger than the planet, perhaps only hundreds of millions of years old, although the full interpretation is still studied. If the rings are young, then Saturn did not always look this way. That is a startling thought. The planet that feels defined by its rings may have spent most of solar system history without the same ring system we see now. The image that seems timeless may be a temporary phase. Saturn may be wearing something it did not always have. It may also be losing it. NASA research has shown that Saturn is losing ring material through a process often called ring rain. Charged, icy particles from the rings can be pulled along magnetic field lines and fall into Saturn's atmosphere. Other processes also move ring material inward. The exact rates and future lifetime depend on models, but the broad idea is clear. The rings are not frozen forever. They are evolving. Some estimates suggest the rings could be gone on timescales of tens to hundreds of millions of years. That sounds long compared with human life. It is short compared with the age of Saturn. Saturn is about 4.5 billion years old, like the solar system itself. If its rings are only a few 100 million years old, and if they may fade within another few 100 million years, then humans happen to exist during a rare moment when Saturn is visually spectacular. That is not sentimental. It is geological time. The rings feel eternal because our lives are short. In planetary history, they may be brief. This is one of the most beautiful and unsettling facts about Saturn. The most iconic sight in the solar system may be temporary. Not temporary like a cloud. Temporary like a chapter in the life of a planet. A future civilization, if it exists far enough from now, might look at Saturn and see a much barer world. The rings could be thinner, darker, or gone. Saturn would still be a giant planet. Its moons would still matter, but the image that defines it for us might no longer exist. That does not make Saturn less beautiful. It makes the beauty more specific. We are seeing Saturn during the age of its rings. The rings also show how gravity can destroy and preserve at the same time. A moon or icy body that drifts too close can be torn apart if tidal forces overcome its self-gravity. Yet once the debris becomes a ring, gravity also organizes it. Destruction becomes structure. This idea will matter later when we talk about moons again, because Saturn's moons do not sit outside the ring story. They shape it, feed it, disturb it, and in some cases may have been involved in its origin. The boundary between rings and moons is not as clean as it first appears. A ring particle is like a tiny moon. A moonlet is a larger piece inside or near the ring. A small moon can clear a gap. A collision can turn a moon into debris. At Saturn, the difference between moon and ring becomes a matter of scale, orbit, and history. That is why the rings are scientifically valuable. They are not only beautiful. They are a natural laboratory for orbiting material shaped by gravity, collisions, resonances, waves, and time. Their flatness comes from collisions and orbital dynamics. Particles with tilted orbits collide and settle into a common plane over time. The result is a disk, a thin, bright, structured disk that appears almost designed, though no design is needed. Gravity and collisions are enough. That is often the deeper lesson in astronomy. Order does not always require intention. Saturn's rings look arranged because physics arranges them. Moons tug, particles collide. Dust falls, magnetic fields guide charged grains, resonances build gaps. Over time, a ring system becomes a record of all those interactions. It is not static. It is not smooth. It is a visible negotiation between order and decay. This is why Saturn's rings are stranger than the version most people were taught. The simple picture is correct enough to point a telescope. It is not enough to understand what the telescope sees. Even their brightness tells a story. Clean water ice reflects sunlight well, which is part of why Saturn's rings look so brilliant compared with the darker ring systems around Uranus and Neptune. If dust and micrometeorite material slowly pollute the rings over time, then their current brightness becomes a clue. It suggests that either the rings are younger than Saturn itself, or that some process keeps them cleaner than a simple old ring picture would predict. The rings are icy debris. They may be young. They are being eroded. They are shaped by moons. They contain waves, gaps, clumps, spokes, and embedded objects. They may come from destruction. They may not last. A child learning the planets may be told that Saturn has rings, as if that ends the story. In reality, that is where the story begins. And just as Jupiter's visible clouds led us downward into hidden pressure, Saturn's visible rings lead us sideways into its surrounding system. The rings dominate the view, but they are not the only reason Saturn matters. In fact, some of the most important discoveries at Saturn did not come from the rings at all. They came from the moons. Titan, with its thick atmosphere and methane lakes. Enceladus, with plumes of water-rich material spraying from cracks near its south pole. Around Saturn, the lesson from Jupiter becomes even stronger. A giant planet is not only a world, it is a collection of environments. Rings show the motion of ice and gravity. Moons show chemistry, oceans, atmospheres, and possible habitability far from the warmth of the sun. Saturn's rings make the planet famous. Its moons may make it one of the most important places in the solar system. Saturn's rings make the planet famous. Its moons make it scientifically dangerous to simplify. That may sound strange, because Saturn has so many moons that they can become a list of names instead of a story. Titan, Enceladus, Mimas, Iapetus, Rhea, Dione, Tethys, Hyperion, Phoebe. Dozens of smaller worlds, fragments, shepherd moons, irregular moons, and objects caught in Saturn's gravity. A giant planet does not travel alone. It carries a whole architecture around it. But two of those moons changed the meaning of Saturn more than most people expected: Titan and Enceladus. The other moons matter too. Mimas carries a huge impact basin that makes it look almost broken. Iapetus has a dark side and a bright side so different that it puzzled observers for centuries. Small shepherd moons help shape ring edges. But Titan and Enceladus stand apart because they do not only add detail to Saturn, they change the questions Saturn asks. One is huge, hazy, and wrapped in a thick atmosphere. The other is small, icy, and spraying material into space. Together, they show why the outer solar system cannot be dismissed as a frozen wasteland. Far from the warmth of the sun, around a planet best known for rings, there are places with chemistry, liquids, oceans, and questions that reach directly into the search for life. Titan comes first because it looks almost impossible for a moon. It is Saturn's largest moon, and it is larger than the planet Mercury. But size is not what makes Titan so strange. Ganymede is larger. What makes Titan unique is its air. Titan has a thick atmosphere, not a tiny exosphere, not a thin layer barely clinging to the surface. A real substantial atmosphere, mostly nitrogen, with methane and other compounds that create a thick orange haze. In the solar system, Titan is the only moon known to have a dense atmosphere. It is not just a ball of ice orbiting Saturn. It is a world with weather, clouds, surface liquids, dunes, rivers, lakes, and seas. But almost every familiar word has to be translated. Rain does not mean water rain in the Earth's sense. Rivers do not mean water rivers. Lakes and seas do not mean oceans you could sail across in a human boat. On Titan, the liquids on the surface are hydrocarbons, mainly methane and ethane. At Titan's freezing temperatures, methane can behave in some ways like water behaves on Earth. It can evaporate, form clouds, fall as rain, carve channels, and collect in lakes and seas. Titan has a methane cycle, almost like a cold alien echo of Earth's water cycle. Earth has water clouds and water rain. Titan has methane clouds and methane rain. Earth has rivers shaped by liquid water. Titan has channels shaped by liquid hydrocarbons. The pattern is recognizable. The chemistry is not. This makes Titan feel both close and distant at the same time. It has landscapes. It has an atmosphere. It has a surface where a future machine can land and operate. Yet the temperature is around -179 degrees Celsius. Cold enough that water ice behaves more like rock. The rivers are not warm streams. The seas are not blue oceans. The haze is not breathable air. Everything familiar arrives in a form that refuses to become Earth. Cassini and its Huygens probe changed Titan forever. In 2005, the European Space Agency's Huygens probe descended through Titan's atmosphere and landed on the surface. For the first time, humanity had pictures from the ground of a moon in the outer solar system. The view was dim, orange and strange, with rounded icy pebbles scattered across a landscape shaped by flowing liquid. Some of its lakes and seas cluster near the poles, especially in the north. Kraken Mare, Ligeia Mare, and Punga Mare are not oceans of water, but seas of liquid hydrocarbons. Their surfaces, shorelines, and possible depths make Titan one of the most Earth-like and un-Earth-like worlds at the same time. Its atmosphere produces complex organic chemistry. Sunlight and energetic particles break apart methane and nitrogen molecules, allowing them to recombine into more complex organic compounds. Over time, this chemistry helps create haze and surface materials that may resemble some of the chemical ingredients thought to have mattered on the early Earth before life began. Again, the wording has to stay careful. Titan is not known to have life. Titan is not being presented as a second Earth. It is a natural laboratory for prebiotic chemistry, the chemistry that can come before biology. That is why NASA's Dragonfly mission is so important. Dragonfly is a rotorcraft lander planned to fly from place to place on Titan, sampling different surface materials and studying chemistry, geology, atmosphere, and habitability. Titan's thick atmosphere and lower gravity make flight more practical there than it would be on many other worlds. A flying machine on a moon of Saturn. That sentence would have sounded like fantasy for most of human history. But Titan makes it physically reasonable. Its dense air gives rotors something to push against, and its low gravity helps the craft stay airborne. Instead of being trapped near one landing site, Dragonfly is designed to explore multiple locations over the course of its mission, moving across a world where organic dunes, impact craters, and icy materials may preserve a record of complex chemistry. The mission is not designed to find animals, plants, or obvious life. It is designed to ask what kind of chemistry Titan has made and how far that chemistry has gone. That is the quieter reason Titan matters. It lets scientists study complex organic chemistry on a planetary scale, not in a small laboratory flask. The moon is cold, slow, and distant, but its atmosphere has been running chemical experiments for immense stretches of time. If Titan is large and atmospheric, Enceladus is small and bright. It is only about 500 kilometers across, tiny compared with Titan, tiny compared with Earth's moon, and almost easy to overlook in a system filled with larger bodies. In a simple diagram, Enceladus would not seem like the place where one of the most important discoveries at Saturn would happen. But Cassini saw something extraordinary. Plumes, water vapor and ice particles spraying from the south polar region of Enceladus, rising from long fractures nicknamed tiger stripes. A small moon was not only frozen and cratered, it was venting material into space. That changed everything. A plume means there is activity, and if the plume contains water-rich material, salts, organic compounds, and other ingredients, then the spacecraft can sample material that may come from beneath the surface without drilling through kilometers of ice. Enceladus became one of the rare places where a hidden ocean might be offering pieces of itself to space. Cassini flew through the plume. Water, rock, chemistry, and energy. Enceladus is powerful because it is small enough to seem impossible. How can such a small world stay active? The answer again points back to gravity, orbit, and tidal heating. Like the moons of Jupiter, Saturn's moons are shaped by gravitational relationships. Enceladus is flexed as it orbits Saturn, and that flexing can help generate internal heat. The exact details of how its ocean stays liquid, how heat moves through the moon, and how the plumes are maintained are still studied. But the key lesson is already clear. Inside Enceladus, tides, rock, water, and heat may create an environment that would have seemed unlikely when moons were imagined as cold leftovers. The ice shell hides the ocean, but the tiger stripes reveal that the interior is not sealed away completely. Material escapes. It becomes part of Saturn's environment. Enceladus even helps feed Saturn's E-ring with tiny ice particles. A moon can feed a ring. A hidden ocean can shape what we see around a planet. Titan and Enceladus also show two different ways to be interesting. Titan places chemistry on the surface and in the atmosphere. It is hazy, complex, and chemically rich in the open, with methane and ethane moving across the landscape. Its mystery is visible as weather and terrain. Enceladus hides its main mystery under ice. Its surface may look simpler, but its plume opens a door into the interior. Its question is not written in orange haze, but in water vapor and ice grains escaping from fractures. One moon asks about chemistry before life. The other asks about an ocean beneath ice. That is what makes the giant planets so important. They do not only create spectacular planets, they create neighborhoods where smaller worlds become more interesting than anyone expected. Around Jupiter, we found volcanoes and ocean candidates. Around Saturn, we found a moon with methane seas and a moon with water-rich plumes. The farther journey gets stranger, not emptier. Saturn's moons make the planet's beauty deeper. The rings catch the eye, but Titan and Enceladus hold the questions. One asks how complex organic chemistry unfolds in a cold atmosphere. The other asks whether a small icy moon can maintain an ocean with chemistry that matters for habitability. And both remind us that the outer planets are not isolated balls. They are systems. This is why Saturn cannot be understood by looking only at the rings. The rings are the famous part. The moons are the deeper surprise. Yet after Saturn, the journey becomes more difficult. Jupiter and Saturn are relatively well studied compared with the next two giants. Spacecraft have orbited Jupiter and Saturn. Cassini spent years at Saturn. Juno still studies Jupiter. We have lived with their data in a way that makes them feel almost close. Uranus is different. The next giant outward is not simply another ringed or stormy planet. It is an ice giant, a world in a different category, visited closely only once, tilted so dramatically that it seems to roll around the sun. Its atmosphere looks calm at first glance. Its color seems gentle. Its name often turns it into a joke. But Uranus may be one of the most important planets we have barely explored. After Saturn's rings and moons, the story shifts to a stranger kind of giant, a planet that refuses to align with the simple rules we expect. After Saturn's rings and moons, the next giant feels almost like a blank page. Uranus does not announce itself the way Jupiter does. It does not dominate a telescope with bands and a giant red storm. It does not hold the eye like Saturn, with bright rings spread across black space. In many pictures, Uranus looks quiet, pale, blue-green, and smooth, almost featureless. That calm appearance is misleading. Uranus may be one of the strangest planets in the solar system, partly because it does not easily explain itself. It is familiar enough that most people know the name, but unfamiliar enough that very few people know what kind of world it really is. It sits between the planets we have studied in detail and the planets we still mostly know from a distance. Jupiter and Saturn have been orbited by spacecraft. Uranus has only been visited closely once. Voyager 2 flew past it in January 1986, gave humanity its first close view, and then kept moving outward. That flyby changed what we knew, but it was brief. There was no long orbital mission, no years of watching changing weather, no repeated close passes over different hemispheres. The spacecraft arrived, measured, photographed, discovered, and left. So Uranus is not only strange, it is underexplored. It is also not a true gas giant in the same sense as Jupiter and Saturn. Uranus is an ice giant, richer in heavier volatile materials, such as water, ammonia, and methane. That word ice does not mean a frozen snowball. Under Uranus's pressure, those materials may exist as dense, hot, exotic fluids hidden below the visible hydrogen-helium atmosphere. Uranus spins on its side. Its axis is tilted by about 98 degrees, so instead of rotating upright compared with its orbit, it seems to roll around the sun like a ball. This is not a tiny seasonal tilt like Earth's. Earth's axial tilt gives us seasons. Uranus takes that idea and pushes it almost to the edge of absurdity. For part of its long orbit, one pole points almost directly toward the sun, while the other faces darkness. Then, over time, the situation reverses. A year on Uranus lasts about 84 Earth years. That means its seasons last for decades. A pole can spend years in sunlight, then years in darkness. The planet's atmosphere, heat flow, clouds, and circulation all have to respond to a geometry that no Earth weather pattern prepares us for. Why is it tilted this way? The simple answer often given is that Uranus may have been struck by a large object early in solar system history, knocking it sideways. That is possible, but the exact story remains debated. A single giant impact, multiple impacts, interactions during formation, or changes involving moons have all been considered in scientific discussions. The tilt is not just a quirky fact. It is evidence of a violent or unusual past that we have not fully reconstructed. Uranus carries a scar in its rotation, but it does not show that scar as a crater. A giant planet has no solid face where an ancient impact mark would remain. Instead, the clue is in the way the whole planet moves. The planet's body remembers something the surface cannot display. Voyager 2 arrived during a strange viewing geometry, with one pole facing the sun and the planet appearing unusually bland. Its cameras saw a blue-green world with subtle atmospheric features, not a dramatic storm-covered disk. For years, Uranus gained a reputation as boring because the close-up images looked so smooth compared with Jupiter and Saturn. That reputation was unfair. Later observations with Hubble, Keck, and other telescopes have shown clouds, storms, bands, and seasonal changes. Uranus is not empty. It is simply difficult to see, and Voyager's flyby caught it during a limited moment, from a limited perspective. This is a recurring lesson in space exploration. A planet can seem simple because we have not watched it long enough. Uranus reflects sunlight weekly from nearly 3 billion kilometers away. Its atmosphere is cold. Methane in the upper atmosphere absorbs red light, helping give the planet its cyan-blue appearance. Haze can soften visible features. From far away, subtle weather becomes easy to miss. But subtle is not the same as absent. The atmosphere has winds, clouds, methane, and changing activity. Bright cloud features have been observed, especially as the planet moved through equinox and different regions began receiving sunlight. Because Uranus has such extreme seasons, long-term monitoring is essential. A few images cannot describe a world whose seasonal clock runs over decades. This is why an orbiter would matter. A flyby gives a snapshot. An orbiter gives a life story. For Uranus, we still mostly have the snapshot. The planet's magnetic field makes the mystery deeper. Earth's magnetic field is tilted somewhat compared with its rotation axis, but it still has a relationship to the planet's spin that feels relatively understandable. Uranus is much stranger. Voyager 2 found that the magnetic field is tilted dramatically compared with the rotation axis and offset from the center of the planet. In other words, Uranus does not have a neat magnetic field lined up cleanly through the middle, like a bar magnet in a classroom diagram. Its magnetic field is tilted, lopsided, and offset. That matters because magnetic fields are clues to interiors. If the field is tilted and offset, it suggests that the dynamo region inside Uranus may be very different from Earth's and different from Jupiter's. Uranus's magnetic field also creates a magnetosphere that behaves strangely because of the planet's sideways rotation. As the planet spins, its tilted magnetic field can sweep through space in a complicated pattern. The solar wind interacts with a magnetic environment that is already misaligned, offset, and rotating with a planet lying on its side. It is difficult to imagine from Earth because there is no familiar comparison. Uranus is not only tilted physically, its invisible magnetic structure is tilted too. The rings add another layer. Uranus has rings, but they are not bright and wide like Saturn's. They are faint, dark, narrow, and difficult to see. They were discovered in 1977 when Uranus passed in front of a star, and the star's light dimmed before and after the planet itself blocked it. Those brief dips revealed rings before spacecraft ever reached the planet. Voyager 2 later imaged them more directly and discovered additional details. Today, Uranus is known to have 13 rings, and the system is much darker and more subtle than Saturn's. The rings are part of the Uranian system, shaped by small moons and gravitational interactions, but they do not dominate the planet's identity because they are hard to see. Saturn's rings shout, Uranus's rings whisper. Its moons whisper too, but they may be important. Miranda, Ariel, Umbriel, Titania, and Oberon were only briefly examined by Voyager 2. Their surfaces show craters, cliffs, canyons, and possible signs of past internal activity. Some research has considered whether the larger moons could have had, or may still have, subsurface liquid layers. They are not as famous as Europa or Enceladus, but they are part of the reason Uranus deserves a real return mission. This is especially important because Uranus and Neptune may be our best local examples of a kind of planet that seems common around other stars. Many exoplanets discovered so far are not exact copies of Earth, Jupiter, or Saturn. A large number fall into size ranges sometimes described as super-Earths or sub-Neptunes, worlds larger than Earth but smaller than Neptune. We do not have a sub-Neptune in our solar system, but Uranus and Neptune give us nearby ice giant laboratories. If ice giants are common, then Uranus is not a joke at the edge of a school chart. It is a key example of a major planetary class. Its interior, magnetic field, atmosphere, rings, and moons could help scientists interpret worlds orbiting distant stars, where we may only know radius, mass, density, and atmospheric hints. That makes our lack of close data feel more serious. We have thousands of known exoplanets and only 2 ice giants close enough for detailed study. One of them has been visited only once. The other, Neptune, has also only been visited once. This is why planetary scientists have repeatedly argued for a dedicated Uranus mission. An orbiter and probe could study its gravity field, magnetic field, atmosphere, rings, moons, internal heat, composition, and seasonal behavior. It could watch the planet change, not simply pass by. It could turn Uranus from a snapshot into a world with a timeline. Why is it tilted so far? How exactly is its interior arranged? Why does its magnetic field behave so strangely? How do its seasons work over decades? What do its rings and moons reveal about its past? Could any of its large moons have hidden oceans or ancient liquid layers? How does an ice giant form, evolve, and hold heat? Uranus is stranger than the classroom version because almost every simple fact opens into a deeper uncertainty. It is blue-green because of methane, but that color hides atmospheric layers and haze. It spins on its side, but the cause is not fully settled. It has rings, but they are dark and subtle. It has moons, but they are poorly explored. It has a magnetic field, but not one that lines up neatly with the planet. It is not an empty blue ball. It is an underexplored ice giant with a sideways body and a lopsided, invisible heart. That is especially true once we leave Saturn. Beyond the bright rings, beyond the familiar giant systems, the solar system becomes more distant, colder, and less explored. Uranus shows us the first part of that deeper outer region, an ice giant that refuses to line up, refuses to reveal its interior, and refuses to be reduced to a single joke or a single color. And then, farther still, comes Neptune. If Uranus is strange because it looks calm while hiding tilted geometry and magnetic disorder, Neptune is strange for the opposite reason. It is even farther from the Sun, receiving even less sunlight, and by simple intuition, it should be quieter. But Neptune is not quiet. The next giant waits in deeper darkness, blue, distant, and unexpectedly alive with wind. The next giant waits in deeper darkness, blue, distant, and unexpectedly alive with wind. Neptune should feel quiet. That is the instinct most people have when they imagine it. It is the farthest known planet from the Sun, moving through an orbit so wide that 1 year on Neptune lasts about 165 Earth years. Sunlight reaches it, but only faintly, so the simple picture is easy to build. A blue planet, very far away, very cold, almost still. But Neptune refuses that picture. It receives only a tiny fraction of the sunlight Earth receives. Yet, its atmosphere is active. It has winds that can race faster than the speed of sound on Earth. It has bright methane clouds, dark storms, hazes, BAMs, and changing features that appear and vanish across time. It gives off internal heat, and that heat helps make the planet more dynamic than distance alone would suggest. Neptune is not quiet. It is a storm world in the dark. That is the first surprise. If sunlight were the whole story, Neptune should be one of the least active places among the giant planets. It is almost 30 times farther from the Sun than Earth is. The warmth that drives Earth's familiar weather is almost gone. And still, Neptune moves. Its atmosphere is mostly hydrogen and helium, with methane giving the planet part of its blue color by absorbing red light. But methane alone does not fully explain the richness of Neptune's appearance. The exact reasons behind the color differences between Uranus and Neptune are still studied, involving haze, aerosols, atmospheric structure, and chemistry. In visible images, that blue color can make Neptune look almost calm, like a polished sphere placed at the edge of the solar system. But that smoothness is partly the limitation of distance. A small disk can hide weather that would look enormous if it were closer. Voyager 2 proved that in 1989, when it became the first and still only spacecraft to fly past Neptune. Before that encounter, Neptune was mostly a telescopic world, a small disk, distant, difficult, and unresolved in detail. Then, Voyager arrived and revealed a planet with structure, speed, and personality. One of its most famous discoveries was the Great Dark Spot, a dark oval in Neptune's atmosphere, large enough to remind people of Jupiter's Great Red Spot, though it was not the same kind of permanent symbol. Voyager saw it in 1989. Later, when the Hubble Space Telescope looked for it in the 1990s, that original dark spot was gone. That disappearance is important. On Jupiter, the Great Red Spot has survived for a very long time, even though it changes. On Neptune, dark storms can appear and disappear on much shorter timescales. Hubble has observed other dark vortices since Voyager, including storms that form, drift, change, and fade. Neptune's storms are not painted marks. They are weather systems with lifetimes. The Great Dark Spot made Neptune feel alive because it broke the idea of a frozen, distant world. A planet so far from the Sun had built a storm large enough to become one of the major images of planetary exploration. It had bright companion clouds nearby, likely formed when air was forced upward and methane condensed into ice crystals. It had motion, depth, and change. And the winds were astonishing. Neptune has some of the fastest winds measured in the solar system. NASA often describes winds on Neptune reaching more than 1,200 miles per hour, or about 2,000 kilometers per hour. On Earth, a storm with a fraction of that speed would be catastrophic. On Neptune, those winds move through a cold hydrogen-helium atmosphere under conditions far removed from anything at Earth's surface. Again, The comparison must be careful. A wind speed number does not mean Neptune feels like an Earth hurricane scaled upward. The air is different. The pressure levels are different. The temperatures are different. There is no solid surface with buildings, oceans, or trees, but the number still tells us something crucial. Neptune's atmosphere is not sluggish. The deeper question is, why? Why should a planet that receives so little sunlight remain so active? Part of the answer is internal heat. Neptune radiates more energy than it receives from the Sun, which means the planet is not simply a cold object being dimly warmed from outside. It still releases heat from within, energy left from formation, and perhaps affected by slow contraction and internal processes. That internal heat is not a full explanation for every cloud or storm, but it changes the frame. Neptune is not just a body under weak sunlight. It is a planet with its own deep energy budget. The atmosphere above is connected to the interior below, just as with Jupiter and Saturn, though the details are different. A distant world can still have a hidden engine. That is something the outer solar system keeps teaching. The Sun weakens with distance, but gravity, pressure, composition, and stored heat do not vanish. Neptune may be far from the Sun, but it is still massive enough to have an interior, an atmosphere, and a long thermal history. The weather we see is the visible expression of all of that. The atmosphere also has a vertical story. Methane ice clouds appear high above deeper layers. Hazy aerosols, temperature structure, and circulation create the colors and features we observe. Dark spots may be linked to deeper cloud or aerosol layers, not simply holes in the atmosphere. Bright clouds can form around vortices when gases are lifted and condense. In other words, Neptune's blue face is not flat. Some layers are visible in ordinary wavelengths, others require infrared observations, spectroscopy, and long-term monitoring. Neptune's largest moon changes the system completely. Triton is strange from the start because it orbits Neptune backward in a retrograde direction compared with the planet's rotation. That is not what scientists expect from a large moon that formed peacefully in a disk around its planet. Its retrograde orbit suggests that Triton was captured by Neptune, possibly from the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. If that is true, Triton is not simply a moon. It is a captured world. A survivor from the outer solar system, seized by Neptune's gravity and forced into orbit around the planet. That capture would have been violent. It may have disrupted any earlier moon system Neptune had. It would have reshaped Triton's orbit over time. Through tides, it makes the Neptune system feel less like a calm arrangement and more like the aftermath of a gravitational event. Triton also surprised Voyager 2 in another way. It was active. At a surface temperature near -235 degrees Celsius, Triton should sound utterly frozen. Yet Voyager saw evidence of geyser-like plumes, dark material rising from the surface and being blown across the ice by thin winds. Triton became one of the few geologically active moons known in the solar system. That is astonishing. A captured icy world orbiting the farthest planet, with a thin nitrogen atmosphere and active plumes in extreme cold. Again, distance did not mean death. Triton's surface is also unusual. It has relatively few impact craters in some regions, suggesting that parts of it have been resurfaced. Its terrain includes smooth plains, ridges, fractures, and a famous texture often called cantaloupe terrain because of its strange, pitted appearance. Scientists have considered whether Triton may have, or may once have had, a subsurface ocean. If Neptune deserves an orbiter, Triton is one of the biggest reasons. A mission to Neptune could also study a captured Kuiper Belt object up close. It could examine how capture changes a moon, how tides affect an icy body, whether Triton still has internal activity, and what its surface chemistry reveals about the outer solar system. Neptune is not only a planet in the solar system, it is also a boundary marker. Beyond Neptune lies the Kuiper Belt, with Pluto and many smaller icy bodies. Neptune's gravity shapes that distant region, including resonant orbits that preserve order where a simple drawing might suggest chaos. Neptune is not just sitting at the edge, it helps define the edge. That makes the lack of a dedicated Neptune orbiter even more striking. We have only one close flyby, from Voyager 2. Everything else has come from telescopes, models, and remote observation. The planet, with some of the fastest winds, a captured active moon, faint rings, dark storms, and deep relevance to the outer solar system, remains barely visited. A whole giant world was crossed once and left behind. Neptune's greatest trick is that it looks simple in a picture. A blue disk, a distant planet, the last giant. But the more carefully we look, the less that image holds. Its atmosphere is fast, its storms are temporary, its heat is internal, its rings are faint, its moon may be captured. Its gravity shapes a distant belt of icy bodies. Its class of planet may be common in the galaxy, while our own close example remains mostly unexplored. So the school version fails again, not because it lies, but because it stops too early. Neptune is blue, but blue is not the answer. It is only the surface color of a world still moving in the dark. And once we have reached Neptune, the outward tour of the 4 giant planets seems complete. Jupiter showed us pressure, storms, and a system of moons. Saturn showed us fragile rings and moons with chemistry and oceans. Uranus showed us a tilted, underexplored ice giant with a magnetic field that refuses to line up. Neptune showed us activity where distance predicted silence. But the deepest mystery of these planets is not only what they look like from outside, it is what they are inside. Because every giant planet we have visited in this journey has hidden most of itself below the visible clouds, below the rings, below the images that made it famous. Jupiter's bands, Saturn's rings, Uranus's color, and Neptune's storms are only the outer signs. The next question goes deeper. What are giant planets made of when pressure becomes extreme enough to change matter itself? What are giant planets made of when pressure becomes extreme enough to change matter itself? That question sounds simple only from far away. From Earth, a planet seems like something you can divide into familiar parts. Atmosphere above, surface below, interior deeper still. For rocky planets, that picture works well enough. Earth has a crust, mantle, and core. Mars has a surface that rovers can drive across. The Moon has ground that astronauts once walked on. The giant planets do not give us that comfort. Their most important regions are hidden beneath clouds that no camera can see through. Jupiter's stripes, Saturn's rings, Uranus's blue-green haze, and Neptune's dark storms are all outer signs. They are the visible skin of worlds whose true mass is buried in pressure. And pressure changes everything. On Earth, hydrogen is a gas. Helium is a gas. Water is a liquid, ice, or vapor, depending on ordinary temperatures and pressures. Methane is a gas at room temperature. Ammonia is something we treat as a chemical with familiar laboratory behavior. Inside giant planets, those familiar identities begin to fail. Materials are squeezed so hard that they enter states we do not encounter naturally at the surface of Earth. Molecules may break apart, electrons may move differently, fluids may conduct electricity. Substances we casually call ice may become hot, dense mixtures. Layers may blend, cores may dissolve, or become diluted instead of remaining as neat balls at the center. This is why a simple cutaway diagram can be misleading. A diagram needs clean colors. Real giant planets may not have clean boundaries. Jupiter is the clearest example because its mass is so enormous. It is mostly hydrogen and helium, but not in the gentle form those words suggest. Near the visible cloud tops, hydrogen behaves like gas. Deeper down, under rising pressure, it becomes denser and more fluid-like. Farther still, scientists expect a vast region where hydrogen becomes metallic, able to conduct electricity. That conducting hydrogen is one reason Jupiter can produce such an immense magnetic field. The field is not a decorative, invisible shell. It is a clue, a messenger from a region we cannot see directly. Saturn tells a related story, but not an identical one. It is also dominated by hydrogen and helium, but it is less massive than Jupiter and has its own interior problems. Saturn gives off more energy than it receives from the Sun, and one possible part of that story involves helium separating from hydrogen deep inside the planet. This is often called helium rain. The phrase can sound almost poetic, but the idea is physical. Under the right pressure and temperature conditions, helium may become less soluble in metallic hydrogen, separate into droplets, and sink deeper into the planet. As that helium moves downward, it can release gravitational energy, helping Saturn stay warmer than a simpler cooling model would predict. It is not rain in the Earth's sense. There are no clouds of helium drifting over a surface. It is a deep, interior process, hidden under pressures where ordinary weather words become metaphors. Jupiter may have its own separation processes too, and both gas giants raise difficult questions about how hydrogen and helium behave at extreme conditions. When Juno measured Jupiter's gravity field, it suggested that Jupiter's deep interior may not match the old picture of a compact solid core surrounded by clean layers. Instead, the core region may be diluted, with heavy elements mixed through a larger part of the planet. That could be a clue to how Jupiter formed, how materials dissolved under pressure, or whether a huge impact early in its history mixed the interior. A fuzzy core is harder to draw than a solid core, but it may be closer to reality. Then the ice giants complicate the story further. Uranus and Neptune are called ice giants because they contain larger fractions of heavier volatile materials, such as water, ammonia, and methane, compared with Jupiter and Saturn. But the phrase ice giant can create the wrong image. It can make people imagine enormous frozen worlds, as if the interiors are made of ordinary ice stacked under blue atmospheres. That is not the right picture. NASA describes Neptune, for example, as having most of its mass in a hot, dense fluid of icy materials, water, methane, and ammonia, above a small rocky core. Uranus is described in similar broad terms. These materials are called ices because of how they behave during formation in the cold outer solar system, not because they are cold, solid ice deep inside the planet today. Under pressure, water is not just water. Ammonia is not just ammonia. Methane is not just methane. They may form hot fluids, ionic mixtures, supercritical phases, or other high-pressure states. The chemistry and physics become difficult enough that even the category ice giant may be too simple. Recent research continues to test whether Uranus and Neptune are more mixed, more rocky, or more exotic inside than traditional models assumed. That does not make the old term useless. It makes the term a starting point. This is why newer interior studies can make the ice giants sound even less settled than their name suggests. Some models give Uranus and Neptune interiors richer in rock or mixed material than older simple pictures. Others emphasize hot, high-pressure fluids. The exact balance is still being tested, because Voyager 2 gave only limited gravity and magnetic data, and no spacecraft has orbited either planet. For Uranus and Neptune, the magnetic fields are especially important clues. Both planets have magnetic fields that are tilted and offset compared with their rotation axes. That suggests their dynamos may not work like Earth's or Jupiter's. Instead of a magnetic field produced near a central core, the conducting region may be in a shell, perhaps where high-pressure water-ammonia mixtures conduct electricity. A lopsided magnetic field may be the shadow of a strange interior. Again, the planet shows us what we cannot enter. We cannot lower a probe through Uranus until it reaches the dynamo. We cannot scoop a sample from Neptune's deep fluid layers. We infer from gravity, magnetic fields, heat flow, density, composition, and models of materials under pressure. Even their heat flow raises questions. Neptune gives off significantly more energy than it receives from the Sun, which helps explain why it can remain atmospherically active so far from the Sun. Uranus, by contrast, emits much less internal heat than scientists might expect for a planet of its type. This difference between the two ice giants is one of the major mysteries. They are similar worlds in broad category, but one seems internally more active than the other. Why? Maybe Uranus lost heat differently because of the same event that tilted it. Maybe its interior is layered in a way that traps heat. Maybe composition, mixing, or formation history created a different thermal evolution. The answer is still not settled. Jupiter and Saturn teach us about hydrogen-helium giants, metallic hydrogen, deep magnetic dynamos, and gas accretion in the early solar system. Uranus and Neptune teach us about volatile-rich planets, high-pressure fluids, unusual magnetic fields, and the blurry boundary between planet categories. They also teach us humility. The deeper we go, the less useful ordinary language becomes. Gas giant sounds simple, but Jupiter is not a loose cloud of gas. Ice giant sounds simple, but Neptune is not a frozen snowball. Core sounds simple, but Jupiter's core may be diluted. Rain sounds simple, but helium rain inside Saturn is nothing like rain on Earth. Words survive by stretching. But if we stretch them too casually, they mislead. That is why the most responsible way to talk about giant interiors is to keep two ideas together. First, scientists know a great deal: broad compositions, masses, densities, atmospheric ingredients, magnetic fields, heat outputs, and many constraints from spacecraft. Second, the detailed interiors are still uncertain because we cannot see them directly. Both are true. The giant planets are not unknowable. They are not fully solved. The clouds show us motion. The rings show us gravity. The moons show us tidal heating, oceans, atmospheres, and volcanic activity. The interiors show us the limits of planetary knowledge. Because beneath the visible features, the giant planets are experiments in what matter becomes when a planet is massive enough. Hydrogen becomes metallic. Helium may separate and sink. Water, ammonia, and methane become hot, dense fluids. Cores may blur. Magnetic fields may tilt and offset. Heat may leak or be trapped over billions of years. A planet becomes not just a place, but a pressure machine. This is the final correction to the school version of the giant planets. They are not big because they are simple. They are big in a way that makes them more complex. Their size does not merely make them larger objects in a diagram. It changes the state of matter, the structure of their interiors, the strength of their magnetic fields, the behavior of their atmospheres, and the fate of their moons. Mass changes the rules. Once we understand that, the four outer giants stop feeling like a row of colored balls. Jupiter becomes a world where hydrogen may turn metallic. Saturn becomes a planet where rings fade and helium may fall through the deep interior. Uranus becomes a tilted ice giant with a magnetic field that hints at strange conducting layers. Neptune becomes a distant active world with heat and motion hidden beneath its blue face. The planets were never only what they looked like, they were what pressure made them. That is why the final step has to pull back. After storms, rings, moons, and hidden interiors, the giant planets still have one more role that may be even larger than their own strangeness. They did not simply form at the edge of the solar system and sit there as ornaments. Their gravity helped shape the solar system itself. The next question is not only what the giants are, it is what they changed. The next question is not only what the giants are, it is what they changed. That is where the story becomes larger than Jupiter's storms, Saturn's rings, Uranus's tilt, or Neptune's winds. The giant planets are not only strange worlds sitting far from the Sun, they are some of the main architects of the solar system. Their gravity shaped the spaces between planets, disturbed smaller bodies, guided moons and rings, and helped decide what kind of neighborhood Earth would eventually live in. They are the reason the outer solar system feels organized instead of random, even when that order was born from motion, scattering, and ancient instability. A giant planet is never just a planet. It is a gravitational force acting across distance. That is easiest to see with Jupiter. Its mass is so large that it outweighs all the other planets combined. Anything passing near it is not simply passing a distant world. It is moving through the influence of the solar system's strongest planetary gravity. This can sound protective at first. People sometimes describe Jupiter as a shield for Earth, a giant planet that catches or redirects comets and asteroids before they reach the inner solar system. There is some truth in that idea, but the full story is more complicated. Jupiter can send objects away from the inner planets. It can also throw objects inward. It can protect, disturb, scatter, and redirect. Gravity does not have intentions. It only changes paths. That makes Jupiter less like a guardian and more like a powerful gatekeeper. Small bodies moving through the solar system can have their orbits altered by Jupiter's pull. Some may be ejected outward. Some may be pushed into new paths. Some may become short-period comets. Some may be removed from dangerous routes, while others may be placed on them. The asteroid belt shows part of this influence. Between Mars and Jupiter, there is no full planet, only a broad population of rocky bodies, fragments, dwarf planet series, and debris from the early solar system. The belt is not the remains of a planet that recently exploded, as old myths sometimes suggest. It is more like a region where planet formation never completed in the same way it did for Earth, Venus, or Mars. Jupiter's gravity helped make that region difficult. Its resonances disturbed orbits. Its presence kept material from simply gathering into one large planet. Over time, collisions, scattering, and orbital structure shaped the belt into the population we see now. A planet that never formed can be part of Jupiter's legacy. Saturn does the same in its own way. Around Saturn, resonances help shape rings and moons. But on the scale of the whole solar system, Saturn's gravity also matters because it works with Jupiter. The early relationship between Jupiter and Saturn may have influenced how material moved during the solar system's youth. Many models of planetary evolution suggest that the giant planets did not simply form exactly where we see them today and remain there forever. They may have migrated. This does not mean scientists know every detail of the early migration story. Different models exist, and some details remain debated. But the broad idea is important. The giant planets helped sculpt the solar system during its formation and evolution. Their current positions are not just addresses. They are clues. Jupiter and Saturn, especially, may have shaped the distribution of small bodies, the structure of the asteroid belt, and the history of bombardment in the inner solar system. Their gravity influenced what was scattered inward, what was scattered outward, and what remained behind. Uranus and Neptune mattered just as much for the outer solar system. Neptune, in particular, helps define the region beyond the planets. The Kuiper Belt begins beyond Neptune's orbit, filled with icy bodies left over from the formation of the solar system. Pluto is the most famous, but it is only one member of a much larger population. Neptune's gravity has shaped that region through scattering and resonance. Pluto itself is in a stable orbital resonance with Neptune. For every 2 orbits Pluto makes around the Sun, Neptune makes 3. In a simple drawing, Pluto's orbit can look like it crosses Neptune's path, which might make collision seem possible. But the resonance keeps their timing organized, so Pluto and Neptune do not meet dangerously. That is gravity as architecture, not a wall, a rhythm. Neptune's influence is also connected to scattered objects, resonant populations, and the boundary between the classical planets and the more distant icy solar system. It is the last giant planet, but it is not just the end of the list. It is one of the main reasons the outer solar system has the structure it does. That is why they matter beyond their beauty. A photograph of Saturn's rings is beautiful, but the deeper meaning is dynamical. A view of Jupiter's bands is beautiful, but the deeper meaning is physical. A blue image of Uranus or Neptune is beautiful, but the deeper meaning is about formation, migration, internal structure, and the kinds of planets that may exist around other stars. This is why the 4 outer giants are not just a chapter after Mars. They are a framework for understanding why the solar system looks the way it does. Without Jupiter, the asteroid belt would not be the same. The delivery and removal of small bodies in the inner solar system would not be the same. Without Saturn, the outer planet architecture and resonance history would not be the same. Without Uranus and Neptune, the distant, icy solar system would not be the same. Without Neptune, Pluto's story would not be the same. Even Earth would not be part of the same cosmic neighborhood. They also give us a way to understand other planetary systems. Around other stars, we have found hot Jupiters, warm Neptunes, sub-Neptunes, super-Earths, eccentric giants, resonant systems and planets arranged in ways very different from our own. Some giant planets orbit extremely close to their stars. Others follow stretched orbits. Some systems seem compact and orderly. Others show evidence of violent migration or gravitational scattering. Studying Jupiter, Saturn, Uranus, and Neptune helps scientists compare our solar system with the many systems now known in the galaxy. Why did our giant planets end up far from the Sun instead of migrating inward and becoming hot Jupiters? Why does our system have 2 gas giants and 2 ice giants? They teach us what one planetary system can become, and they help us recognize how different another system may be. The more exoplanets we discover, the more valuable our own giants become. Even then, we know them unevenly. Jupiter and Saturn have been transformed by orbiters. Galileo, Cassini, Juno, and many flybys gave them depth. Uranus and Neptune still wait for that kind of attention. A single Voyager 2 flyby for each ice giant is not enough to understand entire planets, rings, moons, seasons, magnetic fields, and interiors. This uneven knowledge matters, because it can trick us into thinking the planets themselves are uneven in importance. Jupiter and Saturn feel richer partly because we have returned to them more often. Uranus and Neptune feel quieter partly because we have not stayed long enough. A lack of data can look like a lack of mystery, when it may be the opposite. Jupiter is not only big, it is a pressure world where hydrogen may become metallic, a storm planet with a magnetic environment large enough to dominate the space around it, and a system of moons that includes volcanoes, oceans, and planetary-scale bodies. Saturn is not only ringed, it is a hydrogen-helium giant surrounded by a temporary delicate ring system made of countless icy particles, while its moons include Titan with methane weather and Enceladus with water-rich plumes from a hidden ocean. Uranus is not only tilted, it is an ice giant visited closely only once, with extreme seasons, faint rings, strange moons, and the magnetic field so tilted and offset that it hints at a deep interior, unlike the simpler diagrams we grew up with. Neptune is not only blue, it is the distant active giant with supersonic winds, changing dark storms, faint rings, internal heat, a captured moon, and gravity that helped shape the Kuiper Belt. That is the real reason the giant planets are stranger than we were taught. They are not strange because the school version was false. They are strange because the school version stopped where the real story begins. They become storms, rings, oceans, volcanoes, magnetic fields, resonances, hidden interiors, and ancient gravitational scars. They become systems. They become histories. They become reminders that even in our own solar system, the familiar names are not fully familiar worlds. The giant planets do not need exaggeration. Jupiter is already extreme. Saturn is already temporary and beautiful. Uranus is already sideways and underexplored. Neptune is already active in deep darkness. Their moons, rings, atmospheres, and interiors already carry enough strangeness to last for generations of missions. The universe does not become less interesting when we remove the myths. It becomes stranger because the real physics is better. And somewhere beyond Mars, beyond the asteroid belt, beyond the bright inner worlds we can imagine more easily, those four giants continue their slow orbits. Jupiter turns under its bands. Saturn loses ring material, grain by grain. Uranus rolls through seasons that last decades. Neptune moves through the dark with winds racing across its blue atmosphere. Thank you for watching this journey through the giant planets of the solar system. If you enjoyed it, leave a like, subscribe for more calm space documentaries, and write in the comments which giant planet feels the strangest to you now. Wherever you are watching from, and whatever time it is there right now, I hope the night feels a little larger and the outer solar system feels a little less empty. Good night.